In this video, we're going to take a look at section 3.3 on theory of equations. So to get started, we're going to look at a couple of definitions here. If x minus c is a factor that occurs k times in the complete factorization of the polynomial p of x, then c is called a root of the polynomial equation p of x equals 0 with multiplicity k. So the two terms being defined there are root and multiplicity. A root is an interesting term. It kind of means solution. It's a solution to this equation. It also kind of means a zero of the polynomial, because remember, we learned in the previous section, 3.2, that if x minus c is a factor, that means c is a zero of the polynomial, right? So if x minus c is a factor, the factor theorem told us that c is a zero of the polynomial p of x. Now we're calling c a root of the polynomial equation p of x equals 0. So c is both of these things. C is a zero of the polynomial. It's also a root of that polynomial equation. So root and zero refer to the same set of numbers. They're both numbers that when you plug them into the polynomial, they make the polynomial equal 0. The difference here is the context. So if we're talking about the polynomial itself, then we would call c a zero of that polynomial. If we're talking about an equation involving that polynomial, then we call c a root of that equation. Right? So it's 0 if it's just the polynomial, it's root if it's a polynomial equation where it's equal to 0. All right. So it's a little bit confusing terminology. I have noticed people get those terms mixed up. They interchange them. Even, math teachers, math professors, people that you would think maybe should know better. They're describing the same set of numbers. And so it's very easy to mix those terms or even think of them as just really the same thing. So if you think of them as being the same thing, then you might use them interchangeably without really thinking about it. But there is a slight difference. It's pretty slight. It's 0 when it's just a polynomial. It's a root when it's an equation. And then we have this extra term we're defining, multiplicity. Now, multiplicity is referring to the number of times that factor occurs when you factor the polynomial. So if you get your polynomial factored down and you have a factor like x plus 2 and it occurs 5 different times, that would be the multiplicity of that. That would be the multiplicity of c, of the root c. Essentially, what's happening is if you have the factor x plus 2 5 different times, that factor is giving you the same root, the same 0, the same solution 5 different times, right? So I kind of didn't want to write it out, but I think I should, right? So if we have x plus 2 as a factor 5 different times in our polynomial, I know it's a little bit crazy. I don't know. I wish I wouldn't have picked 5. All right, and maybe there's some other factors here too. Whatever, it doesn't matter. And it's equal to 0. Then we would say that negative 2 is a root of this equation. It's a 0 of this polynomial, but it's a root of the equation. And we get that root from this particular factor. It's just like solving the equation, right? We know how to solve when we have factors. You take the factor, you set it equal to 0, and then you solve for x. Subtract 2 from both sides, we get x is equal to negative 2. Right? That's what this factor produces as the solution. But so does this factor, and so does this factor. Now, normally, we would just ignore that. We would say, well, this is giving me the same answer. It's negative 2. There's nothing new there. It's the answer I already have. And so we don't do anything with that. But we want to start keeping track of that. So you can think of multiplicity as tracking the number of times a solution is occurring when you're solving the equation. And so we would say this solution, x equals negative 2, has a multiplicity of 5 because we are getting that answer 5 different times from these 5 factors that are repeating, right? And so we want to start keeping track of how many times are we getting each answer. Yes, it's redundant. It's the same answer over again, but it's about bookkeeping, right? We need to keep track of how many times this answer is showing up, how many times this answer is showing up. And you'll see why in just a minute. All right. So that's what multiplicity is. All right. So let's go ahead and do this. And I messed up here. Notice the first thing we're asked for is the degree of the polynomial. And I didn't define that term. It's a very simple concept, but I should have put it on the previous screen. And I always forget that I have done this, but I just went over this material in class a couple days ago. So I remember it's on the next page for some reason. I don't know why I put it after that problem, but let's go ahead and talk about this. Then we'll jump back to the example. The degree of a polynomial is just the highest power of the variable, whatever your variable happens to be. So in that polynomial, what's the highest power of the variable? That is called the degree of that polynomial. All right. So here, the degree is 5, right? The highest power, x is my variable. The highest power of x is 5. So that's the degree. That's all there is to that. Very simple. Okay. Then it says, find all of the real and imaginary roots of the equation. Basically, asking us to solve the equation. So if you're asked to find the roots of an equation, just what you want to do is solve the equation. That's how you find the roots. Now to solve this polynomial equation, remember roots are like zeros. Worst case scenario, I don't think you're going to run across this, but theoretically, finding roots is the same as finding zeros of a polynomial, right? We call them roots when we're talking about this as an equation, but those roots are just the zeros of this polynomial. And in the previous section, we learned that sometimes to find the zeros, you have to do the synthetic division stuff. You have to do P's and Q's, make a list of guesses for possible zeros, use synthetic division to find one that gives you a remainder of 0, stop and factor. That could be a necessity on these problems in theory. But I think most of these, they're going to set them up so that you are able to solve them without resorting to the P's and Q's, synthetic division, rational zero theorem, all that stuff. All right. This one we can factor because notice x is a common factor in all three of these terms. We can factor out an x to the third power, and that's going to leave me with x squared minus 6x plus 9. And now that I have it down to a quadratic factor, I can factor it even further without having to use P's and Q's. I need to find two numbers that multiply to 9, add to negative 6. That'll be negative 3 and negative 3. And so we factored it all the way down. Okay. Then we want to solve it, right? We want to find the solutions. Those are going to be my roots to this equation. So I set each factor equal to 0. Right? So I'll start with this one. X is equal to 0. That's one solution. So it's a weird factor. It's just x by itself. But you follow the same procedure. Take that factor, set it equal to 0, and then solve for x. Well, when you take x and set it equal to 0, it's already solved for x. X is equal to 0. We'll do the same thing with these two factors, right? We'll take x minus 3, set it equal to 0, and then we'll solve for x by adding 3 to both sides. And we get x is equal to 3. And the same thing happens with this one, right? We get the same answer again for this factor. We get x equals 3 again. So I'm not going to write it a second time because it's the same steps. You get the same result. But what we want to consider is the multiplicity of that result. So how many times am I getting x equals 3 as a solution? I'm getting that solution twice, right? I'm getting it once from this factor and once from this factor. They both give me this answer of x equals 3. And so since I'm getting that answer twice, the multiplicity of this root is 2. Now on the exam, I've had students where they solve the equation, they get the solutions, which is great, and then they just put somewhere on the test multiplicity whatever. And I think when students do that, they're not understanding that the multiplicity is not for the entire problem. It's not that this polynomial has some kind of multiplicity, right? Each root will have its own multiplicity. So 3 has a multiplicity of 2. So this is not applying to anything else in this problem. It's applying to that number 3. this number 3 has a multiplicity of 2. That root has a multiplicity of 2. So this root should also have a multiplicity. Now, the directions say state the multiplicity when it's greater than 1. So if the multiplicity is just 1, meaning you're just getting the answer once, you don't have to state the multiplicity is 1. You just leave it blank, and it's implied that if the multiplicity is not stated, then it's just 1, meaning the answer just occurs one time. But is that the case here? A lot of students will say yes. They'll say yes. You have one x there. You set it equal to 0. You got x equals 0 that one time. The multiplicity is 1. So even though it says I don't have to state the multiplicity here, I'm going to say it's a good habit to just state the multiplicity for every root, whether it's a 1 or greater than 1. Right? Let's just state it every time. But that being said, the multiplicity here is not 1. Right? So if you think about what this, let's go back to this, right? We have x minus 3 times x minus 3. We left it that way, but we could have written this as x minus 3 squared, right? It's the same factor twice, so I can use exponents to rewrite it. So I'm just writing the factor one time and then using the exponent to indicate that the factor is actually there twice, right? I'm multiplying it to itself twice. And then we saw the multiplicity was 2, right? So this would be another way of writing those two factors using an exponent. And then it turns out the exponent actually matches the multiplicity. And that's not a coincidence. The exponent is the number of times that factor occurs. The number of times that factor occurs is the number of times you're going to get this solution. And so that will be the multiplicity, right? So the exponent always becomes the multiplicity because the exponent tells you how many times you're going to get that root from that particular factor. And that holds true over here as well. This x to the third power really means I have x times x times x, right? If I wanted to write it out, I have x multiplied to itself 3 times. Each of those are factors that give me the answer of x equals 0. So in fact, the multiplicity here is 3. And the shortcut there is just to use the exponent. So if your factor has an exponent on it, then that exponent will be the multiplicity of the root you get from that factor, assuming that it doesn't exist somewhere else in the problem. So if we're writing all of our factors simplified using exponents, then the exponent will be the multiplicity, right, of that root. Okay, let's take a look at this next concept that was on this page that I didn't talk about previously. It's called the fundamental theorem of algebra. Fundamental. If a polynomial equation has positive degree, now remember the degree, that was weird, threw in some extra syllables there, and now I can't talk. The degree is the highest power of x. Now a polynomial, the way polynomials are defined, most of them will have variables, but it is possible to have a polynomial that's just a number. So you could have a polynomial like p of x equals 5. That's a polynomial that has no variables in it, but it still fits the definition of a polynomial. If there are no variables in your polynomial, if your polynomial is just a number, then the degree is 0. In that case, the fundamental theorem of algebra doesn't apply. But that's the lowest it can go, degree 0. Otherwise, it'll have a positive degree. And so essentially, what this is saying is that if your polynomial equation has variables in it, positive degree means there must be some variables in your polynomial. It excludes the polynomials that don't have a variable, right? So if your polynomial equation has a variable to whatever power or multiple of that variable to whatever power and has real or complex coefficients, then there is at least one solution in the set of complex numbers. Right, so this is a really important result that should get mentioned in every college algebra class, but it also might get overlooked. Students might not really give it much attention because it doesn't really impact the problems that we're doing. This is not like a theorem that you're going to take to the next example and use to get the answer. What it does tell you is that there is always an answer. So the way this impacts you is that you should never ever answer any of these problems where you're finding roots or zeros with no solution. The fundamental theorem of algebra tells us there's always at least one solution to all of these equations, all of these polynomials. Right? There's always at least one zero, there's always at least one root to every polynomial, as long as the degree is positive. As long as there's some variable there, there is a solution. So on the test, it would be a bad strategy to just guess no solution on these problems where you're finding roots or zeros. That can never be the right answer. That's what the fundamental theorem of algebra tells us. So that's the way it impacts you. It's not going to tell you how to actually find those zeros or those roots. It just tells you that they exist, that there has to be some. And so don't answer no solution. It's not a valid answer. It will never be right. Okay, that's fundamental theorem of algebra. What is going to be a little more useful to you when you're actually doing these problems is the in-root theorem. If the polynomial p of x has degree n, right? So we're specifying it. It's equal to n. Then when multiplicity is considered, this is why we had to talk about multiplicity. When you count the repeated values of all the solutions, right? Usually we ignore them, but now we're going to make sure to count them. When you count the repetition of solutions, that's the multiplicity, then the polynomial equation p of x equals 0 has n roots. So if the degree is n, then the polynomial equation will have n roots as long as you're counting the duplicates, as long as you're counting multiplicity. We can confirm that this was the case in the example that we just did. Right? So here, the degree was 5. How many answers did I get altogether counting the duplicates? Well, I got this answer 3 times. I got this answer twice, which means I got 5 answers altogether. I got 0 3 times, I got 3 2 times, and so that was 5 answers that I've counted altogether, counting the duplicates, and that adds up to 5, which matches the degree of the polynomial. So that will happen every time. So this is good bookkeeping. This lets you know how many answers you should expect, and it lets you know if you have found them all or not. Right? So when I see that the degree, I'm having trouble saying the degree for some reason, when I see that the degree is 5, I am expecting to find 5 roots to this equation. But I also have to understand that some of those might be repeated values. So in this case, really I only find 2 answers, but because of the repetition, it accounts for 5 of the roots, and that's exactly how many there's supposed to be. So I know there's not any more. There's no hidden roots that I just somehow missed in solving this equation. I've accounted for all of them. Right, so it's very helpful. This rule also applies to zeros. So it's pretty common by the time I'm teaching 3.3 that students have still not started the homework in 3.2, right, the previous section, where you're finding zeros. So I tell them, I know you probably haven't started the homework yet on that previous section. This rule applies to those problems as well. So if you're trying to find zeros, the degree of the polynomial is the number of zeros that you should find when counting multiplicity. All right, so keep that in mind. It'll make sure that you find them all, and you'll know when you're missing one, right? If your degree is 3 and you've only found 2 zeros, you're missing one. You need to keep looking. All right. Okay, now, I forgot about this. I should have adjusted before I started recording. This problem relies on another theorem that I forgot to put in my lecture outline. So I think I should go ahead and, I'm just going to go ahead and write it in. This is what I've done every time. And every time I forget to go back and actually edit my document to include it. So how about I pause the recording so you don't have to sit here and watch me write it out. Okay, so this is called the conjugate pair theorem. If p of x equals 0 is a polynomial equation with real coefficients, and a plus bi is a root of that polynomial equation, then its conjugate, a minus bi, must also be a root. Right, so we talked about conjugates back in chapter 1. It was actually the section from chapter P, but we covered it with chapter 1. And we talked about conjugates there. And the property that conjugates have is when you multiply them together, a complex number with its conjugate, the imaginary part goes away. And we need that to happen here if we want our polynomial to have only real coefficients. So if our polynomial is only going to have real numbers in front of x squared, in front of x to the third power, we don't want imaginary numbers there, then when you have a root with an imaginary number, you need to get that imaginary number to cancel out when all the stuff gets multiplied together. And the way you make sure it gets canceled out is to make sure its conjugate is also included in the calculation. And then when the conjugates get multiplied together, the imaginary number disappears and you get a regular looking polynomial like you're normally used to dealing with, right? With just real numbers in front of all the variables and no imaginary numbers. Okay, so that's called the conjugate pair theorem. Essentially, imaginary roots come in pairs for regular polynomials that have real coefficients. So if you have one, the other one automatically has to be there. And that's kind of what they're testing us on with this particular problem. This is one of my favorite problems in the chapter. It's the reverse of what we were just doing in 3.2, if you will, and what we're about to start doing later in this section, which is they're giving us the zeros. They're giving us the roots. They're telling us the answer. We want to work backwards to figure out what the problem looks like, what the equation would be. So find a polynomial equation with real coefficients that has these given roots. So we have the roots. We want to work backwards to figure out the equation this time. All right, and the two roots that they give us are 9 and 7 minus I. Now be careful about that, because I will have students on the test where they treat 7 as a separate root and I as a separate root. But there's no comma between the 7 and the I. It's a minus sign, and it's one number, right? So 7 minus I is not two separate roots that go in separate factors. It's one number. It has to stay together when we go to set up these factors that are going to produce the equation that we're about to produce. Now, with just a regular, I keep calling them regular, that's really not a very precise term, but with these real roots that don't have imaginary parts to them, these normal numbers, if you will, these are pretty easy to set up, right? And it's based on the factor theorem, and it's based on knowing that if these are roots, these are also zeros, right? And we're told that if a number is a zero of a polynomial, then x minus that number would have to be a factor of that polynomial. So that's how we're going to work backwards from the roots to set up this equation. We're going to take the roots and from them infer what the factors would have to be to make up this polynomial. All right, so if we want 9 to be a root of this polynomial, that means we want the solution to be x equals 9. What factor would give me that as a solution? And a lot of students can figure that out. Well, if I'm getting 9 as my answer, then I would have had to have x minus 9 as a factor. That's the kind of factor that would give me this answer of x equals 9. Right? You would take this factor, you would set it equal to 0, you would solve for x by adding 9 to the other side, and you get that answer, and that gives me that root. Right? Okay, so now I don't know if you want to fill in as much detail as I did here. I'm perfectly fine if you just jump from here to here. If 9 is going to be a root, then x minus 9 has to be a factor. And that's what we want. That's what we need. I don't know why I'm saying more about it. Okay, now, here's where things get a little bit unfamiliar. We enter some unfamiliar territory here. This is another root of the equation, another 0, and it follows the same pattern. Even though we don't normally encounter factors that look like what we're about to write down, it fits the same structure. It follows the same rule. If this number is to be a root to my equation, then x minus that number has to be a factor, right? So if I want this to be a root, then I have to, and a very common mistake I also see on the test is students do not put an x in the factor. They just put 7 minus I in this parentheses. But it has to be x minus this number, 7 minus I. And because it's a complex number with two terms, I'm going to put that in parentheses, right? I'm not doing anything different here than I did over here, right? I'm taking this number and taking x minus that number to create my factor. That's exactly what I'm doing with the 7 minus I. Taking that number, x minus that number is what the factor would have to be. Now, we never see factors like this in the wild, like when we're actually working on problems. You never factor in such a way that you would see something like this, but that is what the factor needs to be in order for us to have the root of 7 minus I. Right? Now, if that's all I do, and I multiply this out, I FOIL it, whatever I'm going to do to multiply it out, I'm going to have the imaginary number in my result. And I'm going to have a polynomial like x squared minus ix, something like that, right? There's going to be I in front of these variables. It's going to be an awkward looking polynomial, not like what we're used to dealing with. And what we really want to create is a polynomial like a normal one that we're used to dealing with. But not only because that's our preference, but the directions specify this, right? The directions say we want a polynomial equation with real coefficients. So this would not be acceptable as an answer in this case. In order to avoid having imaginary coefficients, we have to use the conjugate pair theorem. If we want 7 minus I to be a root to our polynomial equation, then 7 plus I would also have to be a root. They have to come in pairs in order for the polynomial to have only real coefficients. And so they don't tell us that in the problem. We have to know this fact, that if 7 minus I is going to be a root, we need to add 7 plus I to that list. That's how you will be tested on your knowledge of the conjugate pair theorem, right? By being given a problem like this with one complex root, and you having to know you need to add its conjugate to that list. And if we add this conjugate to the list, then we need to set up another factor for this root, right? So if I want 7 plus I to be a root, then I need x minus that number, 7 plus I, to be a factor of the polynomial. All right. Now, when I multiply this out, the imaginary numbers should all cancel out eventually. It takes a while to get there. All right, so that's the setup part. If you get this far in the problem, like on the exam, I do partial credit. I probably give you about I might even be more generous than that, 3 out of 5 points, because you knew to add this to the list. You knew how to set up the factors. That's good. Pretty impressed with that. But if you want to get the rest of the credit, you have to multiply this out, and it's tedious. It's a lot of algebra, a lot of combining like terms, simplifying. If you want to get full credit for the problem. So now to make it an equation, we want to set it equal to 0. So don't forget to put that part in there. On the screen, sometimes it'll already be there. So don't type it in as part of your answer if Math Excel already has it on the screen. So if it looks like this, then you don't need to type in the equal 0 because it's already on the screen. If this isn't here, then you want to make sure you type in the equal 0 in the box. All right. Now that makes it an equation. We want to multiply this out. You want to start with multiplying out the factors with the imaginary numbers in them. And it's going to be a little messy, but then the imaginary numbers cancel out, and then it'll be a little bit easier going after that. All right, so there's a couple of ways to go about this. I like to just keep it the way it got set up to begin with, so just like what you see here, and then use FOIL, because I just think of this as one thing. And this is one thing. So we have 2 factors, 2 items here, and 2 items here. Not 2 factors, I said the wrong thing. We have 2 terms and 2 terms, and that's exactly what FOIL is for, when you're multiplying 2 terms times 2 terms. So you do first, outer, inner, last. The first 2 terms, that's x times x. I'm going to skip past this line here, and I'll write my results down here. That's going to be x squared. The outer terms will be x times this thing. Now it's a positive times a negative, which will be negative. And then we're going to have x times 7 plus I. Then we're going to do the inner terms, which will be this thing times x. And so it's negative times a positive, which is negative. I'm going to put the x in front of the parentheses. So we're going to have x times the 7 minus I. And then we're going to multiply the last 2 terms together. It's a negative times a negative, which will be positive. And then we will have 7 minus I times 7 plus I. Right. Now we still have the x minus 9 to deal with, but I'm going to put that on the back burner for now. Let's get this situated first, and then we'll bring the x minus 9 back into the picture. So to situate this, we're going to go ahead and distribute to get rid of the parentheses. And then here, it's again 2 terms times 2 terms, so we have to FOIL. First, outer, inner, last. Right. So we'll still have x squared. we'll have minus 7x when I distribute the negative, and it's a negative x, right? Negative x into the parentheses, and then minus ix, which again is not something we really want to see. Hopefully it's going to get canceled out here in just a second. Here we distribute the negative x, we get minus 7x again, and the negative x times negative I makes that a plus ix. And then here, when we FOIL, we get 7 times 7, which is 49. 7 times I, which will be positive 7i. Negative I times 7, which will be negative 7i. And then negative I times I, which will be negative I squared. So it's a giant mess. And you might start to despair at this point. Like, this did not go very smoothly at all. But it's about to self-correct here. So we go to simplify. We still have x squared. 7x and 7x combined together to give me 14x, so we'll have minus 14x. The negative ix cancels out with the positive ix, so those just go away. The 7i cancels out with the negative 7i, so those just go away. And then we still have this I squared, but remember from chapter 1, I squared by definition is just negative 1. Minus a negative 1 makes this a plus 1. Right, so let me rewrite that plus sign again. Plus 1, right? And so I have 1 plus 49, which gives me plus 50. And so you see, it actually works out to be a very simple, ordinary looking, I keep calling it normal looking, polynomial. And there's no imaginary numbers now. So by adding the conjugate as another root, we multiply together. It's kind of messy for a while, but then things cancel out and we get back to familiarity, right? We have just x squared minus 14x plus 50, like the kind of polynomial that we're used to dealing with. Now, we still have the x minus 9 to multiply by. But hopefully it won't be as difficult to do now that the imaginary number is out of the picture. And it's still equal to 0, so don't forget about that part too. All right, so we're going to multiply x. Now, it's not really FOIL. A lot of students say, oh, you FOIL here too. That's really not correct. But sometimes students will say that when they just mean multiply. They just call everything, all multiplying with polynomials is called FOIL to them. But really FOIL is specifically for this situation, 2 terms times 2 terms. It's an acronym, first, outer, inner, last. That acronym does not apply because we have 3 terms here. So the more general way that you multiply polynomials together is every term in the first polynomial gets multiplied to every term in the second polynomial. So it's really just distributing. This x gets distributed to all 3 of these terms, like this. And then the negative 9 is going to get distributed to all 3 of these terms. So every term in the first polynomial multiplied to every term in the second polynomial. And so we're going to end up with x times x to the second power, which will be x to the third power. X times negative 14x, that'll be negative 14x squared. X times 50, that's going to be 50x. Then we move on to the negative 9. Negative 9 times x squared is negative 9x squared. Negative 9 times negative 14x, good thing I have my calculator handy, it's going to be positive 126x. And then negative 9 times 50 will be negative 450. And it's still equal to 0. And then you combine like terms one last time. We get x to the third power minus 23x squared, right? Because we combine these two together. And then, not minus, plus, and sorry, I'm not trying to cross it out, just trying to underline it, maybe twice, because these are like terms. We add those together, we get plus 176x, and then the minus 450 just copies down, doesn't combine with anything. And it's equal to 0. And there's our polynomial equation with roots of 9, 7 plus I, and 7 minus I. All right, so that polynomial equation. So it's kind of a fun problem because you're starting with the answer, the roots, and you're working backwards to the problem, the equation. What's I think also kind of interesting about this is exactly how your homework is constructed. So when Math Excel or My Math Lab, whatever we are using at this time, creates your homework problem, that's what we just did is exactly how it does that. So when you're given this equation here, Math Excel or My Math Lab didn't just randomly pick 6 and 17 and 11 and 2. If it's just randomly picking these numbers, chances are we're going to get an equation that will just not be solvable for us. Now, It has a solution, right? The fundamental theorem of algebra tells us there is a solution to every polynomial equation. But being able to find that solution with the methods that we're using isn't always guaranteed, right? These problems are carefully constructed so that when we do the P's and Q's and we do the synthetic division, we're able to find something that works. And if you just randomly pick those numbers, there's a good chance that the synthetic division method will not find anything useful for you, because it's possible that all the roots are imaginary or square roots, and you're not going to be able to find it by that method, right? So this polynomial equation has to be carefully constructed to have findable solutions for us. And the way it does that is it picks the answers first. And then based on the answers, it sets up the factors and then multiplies it out and then presents the problem to you as this. So it picks the answers first, then calculates the problem based on those answers. That way it knows the answers are, of the, how do I want to say it? I don't want to say easy necessarily, but, it knows the kind of answers you're going to get. And then it builds the problem based on those answers. So it knows that you should be able to find them, right? And then it presents that problem to you. But behind the scenes, the code that created this problem already knows the answers, right? It's not that Math Excel, creates the problem and then scrambles to figure out what the answer is supposed to be to that problem. It started off with the answers first, built the problem for you, and then gave you the problem already knowing what the answers are going to be. And then it's waiting for you to type those answers in to see if you're going to get them right. I know this not because I've seen the code behind my math lab. I don't work for that company. I haven't looked at the code. I don't think you can. It's probably all server side. So even on your browser, I know you can click and view source code on your browser, but all that math is taking place not in the browser. It's taking place on their servers, which I can't see that code. I know this because I had to discover this myself. I had some software about 10 or 12 years ago called Scientific Notebook, which I think is still around. And it was, I don't think it's been updated from what I've heard, but it had this component to the software that would let you create exams like how Math Excel works. It generates the problem. So you just give it the parameters, and then it generates the problems based on the parameters that you provide. And I tried doing the problems that way. I tried randomly picking each coefficient, and I'd be like, well, those numbers aren't really going to work out very nice. So then I'd try to constrain, well, pick this one to be whatever you want, but then this one needs to be, something based on this, and then this one needs to be something based on that. And it became very, very complicated. And I was like, how do people do this? And it took me a while to stumble upon the solution, probably longer than it should have, that, I pick the answers that I want first, so I can make sure the answers are nice or exactly the way I want them to be. And then I tell it how to build the problem based on the randomly selected answers, right? So the answers are randomly selected first, then the problem's built on that. And that has to be the way that my math lab does these problems as well. Anyways, that was a little bit of a diatribe, or I don't know, diatribe's not the right word. A little bit of a digression would be maybe a better term for that. But something I think it's interesting. Maybe you do, maybe you don't. You might find it useful to think in those terms at some other, I don't know what your job might be or whatever, but, what can be interesting is, one way of thinking for one discipline, like as a math teacher, finding that solution and finding that useful, could be helpful to somebody else in another circumstance, in another situation, right? That kind of backwards thinking of, if you're trying to create a problem for a test, you're the first thing you're going to think is, let's generate the problem and then figure out what the answer is. That's just kind of where the natural thought process everybody's going to have. But then you realize it's actually better to go backwards, to think backwards on that. Start with the answer you want and work backwards to the problem. And that's not really intuitive, right? That's not normally the first thought most people are going to have when you're creating a math problem. At least I don't think so. But that kind of, thinking outside the box, thinking, in a more non-intuitive way can be useful, not just in math, not just for teachers, but, in a lot of different disciplines. So you might find that kind of, solution outside the box thinking useful in some other area. So that's why I wanted to share it. Anyways, we're almost done with this section. I said in the last video it went a little extra long. I said I'm going to try to keep this one short, and I've probably already failed. So the next few problems, like the one you just saw that I had on the screen previously, we're being asked to find the roots of an equation. And as I've already mentioned several times, roots and zeros are really the same set of numbers. So if you're being asked to find the roots, you're also being asked to find the zeros, right? And to find the zeros, we learned how to find zeros of polynomials in the previous video in section 3.2 by finding P and Q, making a list of guesses, and then start checking those guesses using synthetic division. And we're looking for a remainder of 0. Once we find a remainder of 0, we find a 0 of the polynomial, we can stop and factor, look for the rest of them in the factors. We're going to do the same thing in this section. We're finding roots this time, but it's the same process. Now, in addition to that, this section does introduce a couple of other concepts to go along with the P's and Q's stuff. One of them is called Descartes' rule of signs. The other one's called Theorem on bounds. Now, it's debatable about, I don't know, maybe I'm in the minority on this. I really don't find them that useful. I don't. So what they're designed to do is to take your list of guesses and help you eliminate some possibilities without having to do synthetic division. So for example, Theorem on bounds. If you go through that process, it'll give you a set of numbers, and it says that your 0 or your roots have to be between these two numbers. They can't be any smaller than this. They can't be any bigger than this. And so it kind of helps you narrow down your list, but it takes time to discover what those bounds are. And as I already mentioned in 3.2, usually the more extreme numbers are not the ones that work anyway. So I kind of already exclude those. And I kind of focus on, the more reasonable numbers that are in my list. So I think for the time that you would have to put in to find those limitations, that time could be spent doing synthetic division on a couple of extra numbers, and just, finding it more quickly by just jumping right into the synthetic division. And sometimes those theorem on bounds, don't give you much. It might eliminate only one or two numbers possibly. Sometimes it might do a better job. The Descartes' rule of signs, and I guess you can probably tell from the way I'm talking about it, I don't really know the details of these because I looked into it one time and I thought, well, it's a lot of extra work to teach it, to explain it, and to actually use it on every problem. And I just, at that time, decided I didn't think it was really worth doing. That's my opinion. I do know other teachers are fans of these concepts. They think that they're useful. They like to teach them to their students, and I respect that. It's just a difference of opinion. The Descartes' rule of signs has to do with the sign changes in your polynomial. If the first term's positive and then the second term's positive, but then the third one's negative, that's a sign change. So you can look at the changes, how many times it changes signs, and that will help you know how many negative roots you should have and how many positive roots you should have. But again, it's not perfect information. So you might find that there could be 3 positive roots or 1 negative and 2 positive or something like that. So there's, different possibilities. But occasionally you'll end up finding that the only possibility here is that they're all positive. And if that's the case, that is helpful because then you don't bother checking negative numbers, right? So, for example, if all of your terms are positive, then the root would have to be negative. You'd have to have a negative number in order for the remainder to come out equal to 0, right? So you'd only check negative numbers in that case. You wouldn't check positive numbers. Sorry, I don't know why that came up for no reason. I'm like an hour into this video. My computer's been on all day, and then all of a sudden that pops up to let me know I'm not signed in, which I don't really use OneDrive. I don't know. Have other things that I use Dropbox. I'm starting to use Google Drive a lot more. Anyways, you'll see those mentioned in the directions. Just ignore them. You don't need them to do these problems. So don't worry. You're not missing any essential information. You can just do these problems using P's and Q's, right? So notice it's up here. Descartes' rule of signs, theorem on bounds. Don't worry about those. We're going to use the rational zero theorem to help us find all the real and imaginary roots to this problem. So this is just like what we were doing in 3.2. So the values of P come from the constant term, which in this case is a 2. So P has to be a factor of this number. It has to be a factor of 2. And this is a nice one because there's only 2 things that are possible. 1 and 2. So P has to either be 1 or 2. Those are the only factors of 2. Q has to be a factor of the leading coefficient, which is 6 in this case. What are the factors of 6? We have 1, 2, 3, and 6. That's kind of bad. That's kind of a lot of numbers for Q. And when there's a lot of numbers for Q, sorry, I'm having trouble talking for some reason. When there's a lot of numbers for Q, it means fractions. You're going to be dealing with probably a lot of fractions in your list of guesses. So our list of guesses are constructed by taking every possible value of P divided by a value of Q. So every possible combination of a value of P divided by a value of Q. So I like to start with a particular value of Q. So I'm going to start with Q equals 1 and then divide every value of P by that value of Q. 1 divided by 1 is going to be 1. 2 divided by 1 is going to be 2. And that takes care of Q equals 1. Moving on to Q equals 2, we'll have 1 divided by 2, which will be 1/2. And then 2 divided by 2, which is 1, which is already on my list. So I don't need to write that one again. That takes care of Q equals 2. Now we'll try Q equals 3. 1 divided by 3, that's 1/3. And then 2 divided by 3, which unfortunately is another number. It's a new one. It's not already on my list, so I have to add that one also. And that takes care of Q equals 3. And then Q equals 6, we have 1 divided by 6, which will be 1/6. And then 2 divided by 6, which reduces to 1/3, which is already on my list. And so I don't need to add that one. Now, we have all these numbers here. It's 1, 2, 3, 4, 5, 6. Well, we really have 12 to consider, right? Because we have to consider both the positives and the negatives of these numbers. So here are all the possible rational zeros to this polynomial, which are also all the possible rational roots to this equation, right? Zeros and roots really are almost the same exact thing. All right, now how do I know which ones actually are roots to the equation? I have to check by synthetic division. So I'm going to use synthetic division. The coefficients of my polynomial go across the top. So we have 6, -17, 11, and -2. And then I pick a number off this list. I use it as my value for C. I run the synthetic division, and I'm looking for a remainder of 0. If I get a remainder of 0, I've found a root of the equation. And once you find a root of the equation, you stop and factor. So it's all the stuff that we were doing in 3.2, just basically all over again in 3.3. Okay, now, I don't remember which number works. So we're going to have to take some guesses. In fact, why don't I just, because again, to limit the length of the video, I'll just pause the recording. If you want to do the same, pause the video and make some guesses. Pick some numbers off of this list, do the synthetic division, and let's see if we can find a number that gives us a remainder of... Okay, so sometimes you just get lucky. It was the first number I picked. I decided to try 1/2. I don't know why I picked that number first, and it happened to give me a remainder of 0. So I was expecting to resume the recording and be able to show you that I tried like 2 or 3 different numbers before I found one that worked, but it happened to be the very first number I tried. And so sometimes that'll happen to you as well. Other times, you'll check one number and then another one, then another one. It might take you 4 or 5 guesses before you find one that works. We saw that in the previous video, 3.2, I had a problem where I actually didn't find one until my 8th pick. And so that's probably about the worst it should ever get. You should find something by then. So, all right. So now that I find a number that gives me a remainder of 0, that means 1/2 is a root to this equation. It's one of them. Now, how many am I expecting to find? We learned this earlier in the video. The degree tells me the number of roots that there should be. The degree is 3, so I'm expecting 3 roots, 3 solutions to this equation. I have 1 so far. To find the rest of them, you don't want to go back to this list and keep checking with synthetic division, because it's not guaranteed to be on this list. What if the other 2 solutions are imaginary numbers? You won't find it by synthetic division. The only way you're going to find those solutions is if you stop and factor this one. And then from the factors, you can try to get the rest of the solutions. So my 2 factors here, if 1/2 is a root, that means it's a 0. And if 1/2 is a 0, that means x minus that number must be a factor. Right? That's the factor theorem. Sorry, that x was bothering me there a little bit. Okay, x minus 1/2. The other factor is the quotient from that division, which is going to be 6x squared minus 14x plus 4. Right? It's still equal to 0, right? Because it's an equation. So basically what I just did is I took this polynomial here and I rewrote it like this. I factored it using this information. And now that I have it down to a quadratic factor, I should be able to get the rest of the solutions from that factor. Either by factoring it further, because it's quadratic, I don't have to use synthetic division to factor it, I have other methods I can use, or using the quadratic formula, which may happen on one or two of these problems where you get this factor here and it's not factorable, but you can still solve it by using the quadratic formula, and that'll tell you the other numbers that make this equal 0. All right, because that's what we're looking for. We're trying to find what numbers are going to make this factor equal 0. So I'm trying to find when does this equal 0. Quadratic formula could tell you that as well. But I think this one is factorable. First, we can start by factoring out a 2. Right? 2 is a common factor here. So we'll have 3x squared minus 7x plus 2 left over when I factor out a 2. And I'm just going to leave this factor out of the picture. We already have the answer from that factor anyways, so I don't really even need it at this point. And I'm just going to focus on getting this factored. We can use the AC method, right, which tells me to take a times c, which is going to be 3 times 2, which is 6, and then b is negative 7. So I need two numbers that multiply to positive 6, add to negative 7. That's going to be negative 6 and negative 1. Sorry, I'm being a little bit lazy there. Let me just rewrite those so they're a little more legible. So negative 6 and negative 1. Right. That means I rewrite the middle term as negative 6x minus 1x. The first term stays the same. The last term stays the same. Whoops, I don't know why I put parentheses there. And then we're going to do factor by grouping. So 3x squared minus 6x in one group, negative x plus 2 in the other group. Factor out the common factor. The first group, the common factor is 3x. So we've done this a couple times lately. It's something you're supposed to already know how to do, which is factor polynomials like this. I mean, so again, in college algebra, we don't have a section on how to factor. It's, assumed being in this class that this is something that you already know how to do. However, I have sort of reviewed it here and there as it's come up. But if you're still having a little bit of trouble with this factoring stuff, you should take some time to practice it, because it's going to come up again. I mean, we're already halfway through the course, right? We're in the middle of chapter 3, but it'll come up again later in chapter 3. It comes up in chapter 4, comes up in chapter 5. Just factoring is just always present in this class. It just can come up at any time, basically. All right. Here, there's no common factor, but we can factor out a negative. Not only can we must factor out a negative sign. So factor out a negative 1. That'll make this positive x minus 2. And the purpose of doing that was to make these the same. And because they're the same, we are able to finish this process. If these don't match each other, then factor by grouping is not working. And that means you're not able to factor it. These have to match for us to do this last step, which is factor out the x minus 2. And then what's left over is 3x minus 1. And now I have factored this polynomial. Now there is a 2 here, but that 2 contributes nothing in terms of solving the equation, right? We're still trying to find when this is equal to 0. We set each factor equal to 0, but setting the 2 equal to 0 doesn't give us any solutions, right? It's just you get something false. So really that 2 is kind of useless. You can ignore it. You want to set each factor with a variable equal to 0. So we'll have x minus 2 equals 0 and 3x minus 1 equals 0. And then you solve for x in each case, and this will give us our other two roots, right? So we'll add 2 to both sides. We get x is equal to 2. Here we'll add 1 to both sides. I don't know why that happened. Oh, I hit the wrong button. I'm just gonna leave it. It's not that bad looking. All right, and then we'll divide by 3. And we'll get x is equal to 1/3. All right, and so here are my other two roots. The first one being the 1/2 that I found earlier, right? So remember, the degree is 3. We're expecting to find 3 roots. Here they all are. And I know there can't be any more. I found all of them. So that's how that problem works. All right, so here's the last example. And it's a doozy, right? It's a degree 4. So that means we will have 4 roots. Again, counting multiplicity. So if you get the same root twice, you have to make sure you count it as 2, right? And we have a big number, 275. It's huge. All right, use the rational zero theorem, which is also called the rational root theorem in some textbooks. Descartes' rule of signs we didn't bother with. Theorem on bounds we didn't bother with. And notice we didn't really need those for the last problem either. It would have been a waste of time for me to do Descartes' rule of signs and theorem on bounds because I guessed it right the first time, right? You can't get any quicker than that. So even with those, that would have just added more time to the problem. I was able to find it right away without those tools. Okay, so P has to be a factor of the constant term, which is 275. And this is a tough one, but we're going to have to break it down. Now, 1 is always a factor. 2 doesn't work here because it's not an even number, so 2 is not a factor. But let's check 3. And the way you check is there's some shortcut ways of knowing, but probably the easiest way to check is use a calculator. Take 275, divide it by the number you're checking to see if it's a factor. And if it divides evenly, then yes, that number is a factor. So I divide by 3. It doesn't divide evenly by 3. So 3 is not a factor. 4 will not work, again, because it's not an even number. 5 definitely will, right? Because it ends in 5. So 5 will divide into that. I'll go ahead and add that to my list, but it's also worth dividing in your calculator because the other number that you get will be another factor, right? So 5 is a factor because it divides evenly into this. When you divide these, the answer you get is another factor, which I'm getting 55. Now that's helpful to me because for 55, I can see pretty obviously here, 11 works, right? 11 divides into 55, which means it should divide into the original number. So let's go with 11, right? So 275 divided by 11 gives me 25. Right? And so notice how these kind of pair together, right? 11 times 25 is 275. 5 times 55 is 275. 1 times 275 is 275. And I think that's all of them. I know yesterday on the video I did, I say yesterday, but on the video I did previously, 3.2, there was a problem where I missed one of the factors. And I definitely don't want to make that mistake again. So I want to think carefully for a moment just to make sure there's nothing else I'm missing. But if you look at these, like 25, the only factors of that are 5 and 5, right? Which we already have here. 55 is 5 and 11. We already have those. So it seems like we've found them all. I'm pretty sure that's all of them, all right? So while that's a big number, it doesn't have a lot of factors, actually. That's kind of surprising. Now, Q has to be a factor of the leading coefficient, which is a 1, right? There's no number here. That means it's an invisible 1. The only factor of 1 is the number 1. That's best case scenario, right? If Q is equal to 1, that's the easiest situation to occur. I don't know. I'm not saying that right. Again, when I get near the end of the videos, I'm not very good at my word choices. So I'm sorry about that. But Q equals 1 is kind of best case scenario for us, right? Because that means no fractions. So I take every possible combination of a P divided by a Q, but since Q can only equal 1, when I divide all these numbers by 1, I just get these numbers back, right? 1 divided by 1 is just 1 again. 5 divided by 1 is just 5 again, so on and so forth. So I'll get 11, 25, 55, and 275. And then we have to consider both positive and negative of those numbers. So these are all of our guesses as to what could be zeros to this polynomial, which means these are our guesses for what could be roots to this equation. Now in 3.2, I almost said yesterday again, because I recorded that one yesterday. And you might notice I'm wearing the same shirt in that video, but I don't wear this shirt all day long. I wear this shirt to record the video, then I change into more comfortable clothes. So I'm not like wearing the same clothes every day. I'm not to that point yet with the lockdown, quarantine, isolating stuff. Anyways, on that video yesterday, I said there was another degree 4 polynomial. And I said, I think 1 is always an answer to this one. And I was wrong. And 1 didn't work. And I think that was the one where it took us a while to find one that did. And now that I'm at this point in the video, I realize this is the problem that I was thinking of. The problem where 1 always works is in section 3.3, not 3.2. And it's the degree 4 one. And this is the one I like to put on the test. And I feel bad because this number, it's kind of like this was a bad one and it could be worse. This number can be a big number and it can be really hard to find all the factors. So what I like to tell students as a hint for the test is that for this particular problem on the test, check 1, because I'm pretty sure this is the one where 1 is always one of the answers. So let's find out. Let's find out together. So we're going to check 1. That's going to be the guess I'm checking from my list. That'll be my value of C. Across the top, I'll have the coefficients here, which will start with 1, negative 12, 36, negative 300, and 275. That was a really weird 300. Okay. Now, something else I noticed, because I don't always rewatch my recordings. I'm not quite at that point yet where I'm like editing very closely. I'm just trying to get them all recorded because I'm trying to get it done as quickly as I can. And I notice a couple times though when I'm watching that my computer glitches and the audio will just cut out and have this like really distorted sound. And I'm pretty sure it's my computer that's doing that, because it'll do that to me like when I'm just like, watching YouTube or whatever. The cursor just locks. Like my computer locks down for like 20 seconds, sometimes 10 seconds. And then I can move the mouse again. So I don't know why it does that. It's a new computer. I'm not sure why it's glitching on me that way. But I noticed the last time when it did that glitch, it also glitched on the writing. So when I wrote something funny like that, the audio glitched at the same time. So I'm wondering if every time that happens, the audio is glitching. And if that's the case, I am really sorry. I know that might be annoying to have to, hopefully you're still learning from them. Like, it's not so bad that you can't understand what I'm trying to say overall, because I repeat the same things over and over anyways. But I do apologize having to listen to that glitch. It was bugging me, so I'm sure it must be bugging you guys as well. And I'll try to, in the future, if we'll see, try to do a better job of editing my videos. But I don't know what I would do in that case, because like I could edit out the glitch, but then a piece of the audio is just missing where I go from one part of the sentence to another and the middle piece would be missing. So it still wouldn't really make sense. All right. Anyways, drop the 1 below the box. 1 times 1 is 1. Add these together, you get negative 11. Negative 11 times 1 is negative 11. Add these together, you get 25. 25 times 1 is 25. Add these together, you get negative 275. Negative 275 times 1 is negative 275, which is perfect, because that's exactly what we needed to get 0 as a remainder. So as I suspected the wrong one earlier, but this one I was right about. 1 works, and it always works on this degree 4 problem. It didn't work on the last problem we did, but this one particular one that's degree 4, it seems like they always have 1 as one of the answers. So I find a solution, I stop and factor, right? I don't go back to my synthetic division yet. I factor first to see what the factors look like. So here, the 1 as a root gives me x minus 1 as a factor. The other factor will be this quotient, which actually this time starts with x to the 3rd power. Right? This is 1x to the 3rd power minus 11x squared plus 25x minus 275. Right? And it's still equal to 0. And sorry, I forgot the parentheses there. All right, so that's the other factor. Now, I promised I'd try to keep this video as short as possible. So I'm not going to do what I did in the previous video where we had a, so you have a degree 4 polynomial. You find a root that works or a 0 that works. You factor it. Then your biggest factor is a degree 3 polynomial now. And in some cases, you'll have to do more synthetic division to break that down until it's degree 2. Because once you have it down to degree 2, that's quadratic. That's the point at which you don't need synthetic division anymore. You know how to factor or solve a degree 2 polynomial without all these extra tools that we're learning in this section. But we have to get it down to degree 2 first before we can reach that level of certainty, before we can, maybe that's the wrong way to say it, before we can be certain to be able to solve it without synthetic division and P's and Q's and all that stuff. However, in the video I did in 3.2 and here, this degree 3 polynomial is such that factor by grouping will work. And so for this particular problem, I'm giving you a couple of big hints here. 1 is always one of the solutions. Once you find that solution and you stop and factor, the factor you're getting from the quotient can be factored further by doing factor by grouping. So you don't have to go back to doing more synthetic division. You can just factor this the rest of the way to get the rest of your roots, right? So again, this doesn't always work. You'll know it's working if after you group them and you factor out the common factor, if you have the same thing left over in both parentheses, then it's working. Factor by grouping works, and you can finish factoring. If what's left over in the parentheses is not working, then if what's left over in the parentheses does not match, then factor by grouping is not working, and that means you cannot factor it using that method. And if you can't factor it by factor by grouping, when it's degree 3, you have to do the P's and Q's. You have to do more synthetic division. So see the video from 3.2 for that, because in 3.2, even though we could have factored this by factor by grouping, I still use synthetic division to show you what that would look like. Right. But this one, I'm ready to be done with this video. So I'm just going to go ahead and use factor by grouping because it'll be faster if I stop talking about it. So group the first two terms, group the second two terms. Right, factor out the common factor in the first group, which is x squared. That's going to leave me with x minus 11. The common factor here, you might think 5. That is a common factor, but the greatest common factor we should look into is 25, and 25 does work. So you factor out 25, and when you check your calculator, this is obviously just going to be x, but this one, divide this by 25, and you get 11 again. And that's necessary for this to actually work out. If these did not match each other, then this would not be an option for me. And the only other option, if this doesn't work, is to go back to this list, do more synthetic division until you find another remainder of 0. But thankfully, it did work out, so I can factor out the x minus 11 since they're the same. That leaves me with x squared plus 25. All right, and I still have this factor here of x minus 1. I'll go ahead and copy that down. Still equal to 0. And that's as much factoring as you can do with this problem. So the next step is to set each factor equal to 0 and solve to get your roots. So we have x minus 1 equals 0, x minus 11 equals 0, x squared plus 25 is equal to 0. Right, now x squared, this is quadratic, but this is not factorable. So we can't break that down any further. So we just have to take what we have and set it equal to 0 and try to figure out a way to solve it. All right. This we can solve by adding 1 to both sides, and we just get the answer. This one's kind of boring because it's the answer we already knew. It's the one that we found from synthetic division, x equals 1. But this is new, right? We add 11 to both sides to solve this equation, and we find that x equals 11 is a root to the equation. Right, now, how many are we supposed to find? The degree is 4, so we should be finding 4 roots. Here's 2 so far. The remaining 2 we will get from this, right? Because this is degree 2. I should be getting 2 roots from this equation. And when I add that to these 2, that's 4 altogether. Now to solve this, it's quadratic, but we can just solve it for x. Get x by itself by subtracting 25 to the other side. We get x squared equals negative 25. And then take the square root of both sides to solve it for x. And we will get x equals, now remember, when you take the square root of both sides, we've done this many times throughout this course, you have to put plus or minus. So that's why we're going to get 2 solutions here. And then the square root of negative 25. So the square root of 25 is 5, but because it's negative, the answer here should be imaginary. And so these 2 you would never find from synthetic division because they're imaginary. So if your strategy is to find all of the roots or the zeros by just synthetic division with all the numbers in your list of guesses, on this problem, you would find 1 and you would find 11. It would take you a long time because you have a lot of numbers to check, but you would never find these 2. And you should know that you're missing some because the degree is 4. You should be having 4 answers. You only get 2 from that list. These 2 you can only ever find if you're factoring as you're finding these roots. All right, so that concludes the video on section 3.3. Thank you for watching.